Thank you very much for watching this presentation. The title of my presentation is Japan Lunar Navigation Satellite System, LNSS, and its contribution towards Multi-GNSS. My name is Masaya Murata from Japan Aerospace Exploration Agency. NASA, ESA, JAXA are now developing lunar command nav GPS systems for the moon, and this slide shows their respective system names and expected years of their first satellite deployment. ESA system is called LCNS, Lunar Communications and Navigation Services. NASA system is called LCRNS, Lunar Communications Relay and Navigation Systems. The JAXA system is called LNSS, Lunar Navigation Satellite System, and today I will talk about the overview of our LNSS, our ongoing collaboration with ESA and NASA, and demonstration mission and planning. These three space agencies are now working towards the establishment of Moon GNSS called LANS, Lunar Augmented Navigation Service, and the concept of the LANS is shown in the slide. The point is, even though Japan, Europe, US satellites will be developed and deployed by different agencies and companies, all of these satellites will broadcast standardized navigation signal called augmented power signal, AFS, to form the LANS. In this way, lunar users will not have to differentiate each system, and interoperability among the respective lunar PNS systems will be guaranteed from the get-go. This concept is quite important because it is challenging to deploy the specific number of satellites around the moon by each space agency. Through this international collaboration, we can achieve the provision of a high accurate PNG service for lunar users. Regarding the JAXA system, LNSS, it was designed to become the GPS-like system for the moon, and this slide shows the satellite constellation. We will use two stable moon orbits called EL4, elliptical lunar frozen orbits, and for each orbit, 4 satellites will be deployed. Therefore, the total number of the satellites becomes 8 for the LNSS, and these LNS satellites will broadcast one-way navigation signals, AFS, for lunar users. Our initial service region will be the lunar South Pole region, same as NASA and ESA lunar PNG systems, where US Artemis Base Camp and global exploration will be expected. Our LNSS also function as a data relay satellite between the moon and the Earth, but today my presentation is focused on the PNT aspect. As mentioned, our LNSS constitute the LANS together with NASA LCRNS, ESA LCNS, and we JAXA are now planning to deploy our first LNS satellite in the year 4 in 2028 and demonstrate the interoperability and the accuracy of the initial LANS, which will be explained later in this presentation. Note that our initial first LNS satellite has a navigation payload only. And in 2031 and later, we are planning to deploy our second LNS satellite that has both navigation and communication payloads and demonstrate the optical communications between the moon and the Earth. To provide the PNT service for lunar users, the orbit and clock information of the LNS satellites should be determined as accurate as possible. So we have investigated several approaches for this orbit and clock estimation problem, and our current design is focused on using the GNSS weak signals. As shown in this slide, because the GNSS satellites all pointed towards the Earth center, their navigation signal that pass the umbrella of the Earth will only reach the moon region, and the LNS satellite will be navigated based on these GNSS weak signals. And according to our simulation results, the CC of about 20 meters after the future convergence was confirmed by this approach. So this approach will make our LNSS highly autonomous because the amount of the Earth station operations will be greatly decreased. And this slide shows the expected LNSS single point positioning accuracy at the South Pole region. Here, the left figure showed our LNS constellation, and for receiver located at the South Pole, we performed the single point positioning accuracy evaluation using the LNS shoot range measurements. And these results indicate that the average estimation errors for the 3D positioning was about 38 meters, while that for the 2D horizontal positioning was about 14 meters. So these numbers clearly show the feature of our LNSS, and indeed, our satellite constellation was designed to provide the high accurate horizontal positioning accuracy at the South Pole region. And the right figures show the positioning to the horizontal positioning errors versus time, and for most of the time epochs, to the horizontal positioning accuracy, less than 40 meters were confirmed. And this slide shows the expected navigation accuracy by our LNSS in the South Pole region. And this time we assumed an object that moved in a circular manner with a velocity of 3 meters per second at a south altitude of 85 degrees. And we evaluated the navigation accuracy for this moving object. And these two graphs below show the confirmed navigation accuracy for its moving object using the LNS pseudo length and pseudo length rate measurements. The lower left graph plotted the 3 and 2D positioning accuracy versus time epochs, and after the future convergence, less than 15 meter accuracy for the 3D positioning and less than 10 meter accuracy for the 2D positioning. 2D positioning were confirmed respectively. The lower right graph plotted the clock estimation accuracy for this moving object, and less than 20 nanosecond accuracy. Clock estimation accuracy was confirmed after the filter convergence. So as for the convergence time, the 2D horizontal positioning accuracy required about 1 hour to be converged, which means after 1 hour, less than 10 meter 2D positioning accuracy would be expected by using OLNSS. I will next talk about our ongoing collaboration with ESA and NASA and on the LunarNet Interoperability Specification, LNIS. And this photo was taken at the Lunar PhD panel session at the Ion Genesis Plus last year. And in this panel, the representatives from ESA, NASA, JAXA presented their respective lunar PNT systems, the LunarNet Interoperability Specification, LNIS, and the LANS, and the status of our ongoing international collaboration. The second person from the right is me, and it was a great honor to participate in this first ever Lunar PNT panel with Lunar PNT leaders from NASA and ESA. The LNIS draft version 5 is now available on the internet, and this document includes the important information as shown in the slide, such as the concept of length, the message format of the augmented force signal, FS, and the signal frequency and power, and signal in space error C3 requirement for the lunar service providers LNSPs. The lunar reference system and lunar time system standards will be also published as the applicable document to this LNIS. Or LNSI or JAXA LNSS comprised with the LNIS to become interoperable and comparable with the other lunar service providers. And thanks to NASA and ESA, JAXA has recently joined the LNS working group and is now working with NASA and ESA for the publication of the LNS version 5 this year. I will next talk about the plan of our LANS interoperability and PNT demonstration mission currently targeting in 2028. JAXA is now planning to launch and deploy our first LNS satellite and LANS receiver to the moon in 2028. And this slide shows the deployment overview, and using the JAXA rocket and Japanese small lander, we will deploy our first LNS satellite in the moon orbit, year 4, and we also place the LANS receivers in the lunar South Pole region. Using this mission, we are now proposing the first ever ESA NASA JAXA LANS interoperability and PNT demonstration. In the year of 2028, one ESA LCNS satellite and a few NASA LCNS satellites are expected in the moon orbits. And using the LANS receiver to be located at the South Pole region, augmented force signals, FS, from these satellites will be analyzed, and the LANS interoperability will be demonstrated. In this mission, we are also planning to place the laser reflector LRR at the South Pole region to obtain the precise position of the LANS receiver. And based on the precise position and the clock information of the LANS receivers, we will evaluate the signal in space error, CC, for each satellite forming the lens, and also evaluate the lens PNT accuracy. So this demonstration mission will contribute to both the first ever lens interoperability demonstration and also the lens PNT accuracy evaluation in the actual moon environment. And this slide shows the 3 major steps for this demonstration. And the first step is the mission data acquisition, as shown in the pink here. And this mission data will be comprised of the lens augmented for signal, lens receivers, PNT solutions, and the GNSS weak signals. And this mission data will be transmitted to the Earth for the in-depth analysis. And the second step is the ground truth data calculation by Earth stations shown in the orange here. And these ground truth data are comprised of the precise lens satellite orbit and clocks, and the precise lens receiver position and clocks. And these ground truth data will be obtained by X-band ranging, DDOR, delta differential one-way range using the Earth station. We are also planning to use the laser ranging to increase the accuracy of the ground truth data. Then comparing the acquired mission data with the calculated ground truth data will enable the evaluation of the CCs for lens satellites and the evaluation of the lens PNT accuracy. So these are the overview of the demonstration procedure for the proposing lens interoperability and the PNT demonstration mission. Okay, to conclude, the JAXA LNSS, ESA LCNS, NASA LCRNS will comply with the LNS and together form the lens that become the Multi-GNSS. These 3 space agencies encourage the proposed lens interoperability demonstration mission in 2028, and they are currently assessing their respective participation. The lens receiver to be located at the South Pole region will receive all lunar service providers augmented for signals and send them back to the Earth for the in-depth analysis. And in this mission, as mentioned, a laser reflector will be placed in the South Pole region as well for the precise position estimation of the lens receiver. And we expect that these laser ranging data will be also utilized for the refinement of the Lunar Reference System, LRS, which becomes one of the contributions that this demonstration mission will provide to the Lunar PNT international community. That's everything from my talk today, and thank you very much for hearing.